Uh, so this is me, John, and I want to present our work in collaboration with Berkehan, Tatli, and my PhD advisor Tuncay Yalcinkaya. So this is somehow in parallel with the previous presentation. So I will be talking about failure in dual phase steel microstructures using a phase field fracture framework. So here's the outline for the presentation. So the dual phase steels, as many of you know, are two-phase materials with soft ferrite phase and a hard martensite phase. So this steel is mainly used in automotive industry because of their high strength hardening in the early stage and good elongation properties. So, however, this two-phase microstructure leads to complex micromechanics, and based on the martensite volume fraction, martensite morphology, it can lower the formability of the material. So it is actually important to understand the mechanisms between this in this regard. So in literature, mainly there are three types of failure mechanisms in dual phase steel. So they are listed as ferrite decohesion, ferrite martensite decohesion, and martensite cracking. So what people assume is that as you increase the volume fraction of the martensite, you get bigger islands of the martensite, and they're more connected, which can lead to the cracking of the martensite. And when they're in low volume fraction, they're more discrete. Therefore, martensite ferrite decohesion or ferrite debonding is more important. So what is interesting is that it's not always clear where these cracks start. So in a recent work, they took this picture just before the crack initiation where the stress drops. So they discussed that although there are two martensite islands near the crack, there could be also a ferrite grain in like ligaments between them. So the crack initiation is not clear. The location of the crack initiation is not clear in this case. So how people model this issue, there are mainly very complex and very basic approaches. So the localization methods, they use the prediction based on plastic strain localization of microstructures. So they create the microstructure from EBSD scan, and they using finite elements, they pull the material and check the localization points to model the crack initiation. And there's also representative volume element simulations on like simplified models as you see on the left bottom side, or like in this case with crystal plasticity and colloidal zone elements from our group, they try to simulate cracking in dual phase steels. The thing is for the localization methods, what's interesting is that for DP steels before localization, actually there is damage initiation. So if you base your predictions only on the localization, it wouldn't be so physical. And for this very complex models, then you enter into parameter identification, which is very hard because you have two phases. And for example, for this model, you have grain colloidal zone elements between ferrite and martensite. And also there's a model for martensite cracking as well. So there are many parameters that you need to decide. Which can lead to a non-unique parameter set for your analysis. So what we want to do is do something in between with little parameter sets and a damage model. As I said, so we want to investigate the microstructural features on ductile failure of dual phase steels through finite element analysis. And we are using a phase field framework for this. And we want to develop a consistent framework that can link the microstructural features to the macroscopic forming limits or failure. So in this work, I'm using a J2 plasticity, a von Mises plasticity model for the two phases, using a phenomenological hardening rule, an isotropic hardening rule actually. So this is mainly taken from the literature for the DP600, and we calibrated this calibrated the hardening for two phases to achieve the homogenized microscopic curve. So let me talk about the phase field fracture framework very briefly. So this phase field microstructure is also called as crack phase field. So in the phase in this model is actually the crack. So it is a diffuse crack approach, as you see. Instead of a sharp discontinuity in the model, we have a diffuse description of the crack. And at the top, when the phase field parameter reaches 1, the material fails. So the advantage of this framework for the dual phase steels is that you can model crack initiation and propagation in the microstructure without needing any cohesive elements or any other criteria, because you're solving another phase in your model, which can, the crack can enucleate anywhere and propagate through grains. So we implemented this model in Abaqus through coupled temperature displacement elements. Here, the temperature is used for the phase field interchangeably, because we are defining the heat generation to solve the phase field equation. Which is very convenient, because then you can use all the features, inbuilt features of Abaqus. So just to understand how this model works, we are using a threshold-based model, which means that with this energy dissipation, plastic dissipation threshold, we can control the ductility of the model by increasing or decreasing it. So we will give two different values for martensite and ferrite to define their ductility. So a little bit of previous work. So we actually started this work with crystal plasticity and the phase field together by simulating the microstructures that are generated randomly. So these morphologies does not belong to a real case. However, we see that the computation times significantly increase, and in terms of the overall ductility, when you want to fit it to the macroscopic thing, this randomness of the grains and the grain orientations does not affect the model's performance much. So we will continue, as I said, with the J2 plasticity model to reduce the computation times, at least for this presentation. So I will talk about how we create the finite element models. So we took this microstructure from the literature and using the open source of OOF2 software, that takes basically processes this image and creates different microstructures. We took like 3 regions in this from this picture, and as you see, there are 3 morphologies that basically models the real microstructure. With there's a little bit of scatter in the volume fractions of the martensite, but at the end, we saw that it doesn't affect that much of the macroscopic response. So as I said, we are using Abaqus to do the simulations, and these are 3D models, the plate models. So there's a thickness, a very small thickness in the model, and we are using a coupled temperature elements to model phase field. The boundary conditions, so we are using 3 different stress states: the uniaxial tension, biaxial tension, and plane strain tension. For this, all the models, we are using symmetric boundary conditions on the left and the bottom. And the nodes on the top surface and the right surface are coupled to a master node to deform them homogeneously throughout the deformation. For biaxial tension, of course, we are pulling from the 2 sides, and plane strain tension, the top side as well is fixed in a symmetry direction. So they correspond the uniaxial tension with triaxiality of 1/3, and for the biaxial tension, triaxiality is 2/3. So I will talk about how we define the parameters for this model. As I said, first of all, we have this experimental curve there, and we fit the model martensite and ferrite hardening curves to match the experimental data to the stress strain data. Then the parameters for the phase field model, since this is a DP600 with relatively low martensite fracture, we assume that the cracks actually initiate in ferrite grains. So we first determine the failure of the phase field parameter of the ferrite phase based on the macroscopic predictions. Then for martensite phase, we assume some very small ductility range, around 0.02 maximum plastic strain, and this corresponds to these values. So these are the elastic parameters, these two. This is the fracture toughness of the model. This parameter mainly controls how fast the degradation happens in this model, and also it controls if the material cracks in the elastic phase. So you can also crack the material for the martensite, of course, in the elastic regime. And we took a length scale as 10 to the minus 3. This is mainly taken to be 5 times bigger than the element size. And these are the plastic limits for this is an energy term, of course, for the two phases corresponding to these two data. So I will talk about the results. First, the crack initiation. So this is the first morphology, by the way, and there are mainly 4 locations where the cracks initiate. And here I am plotting the phase field parameter from 0 to 1. And these red portions are martensite grains. So as you see in the black portion, the main crack initiates between 2 martensite islands that are very close to each other and they are elongated in the loading direction. As you see in this second and secondary cracks, there's also 2 martensite islands and small ferrite ligaments between them. And there's also a third location where the martensite grain is actually started to accumulate damage. And this martensite grain is also elongated in the loading direction. And when you pull it in the vertical direction, in the y-axis, let's say, the same observations can be made. For example, this martensite grain damage initiation occurs, and in this top region, we see that there is again a small ferrite region between 2 martensite islands. So we can conclude that the cracks mainly nucleate between martensite grains that are elongated in the loading direction. So if you check another case where in the morphology 3, something interesting happens. In this morphology there are 2 big martensite islands and a small martensite connection between them. So in this morphology, the martensite directly cracks with another, and there is no another secondary crack initiation. And if we check the biaxial tension and plane strain tension cases, they basically just the crack initiation location basically changes, but also again they are in between 2 martensite grains. If you check the crack propagation, this is the good thing about the phase field model. You can just do nice pictures of crack propagation with this model. On the top case, we just show the uniaxial tension cases. They are always on slanted with respect to the loading direction, and they mainly go through around the martensite grains and in ferrites. For the bottom two, these are the plane strain tension and the biaxial tension case. And for the plane strain tension, we have a vertical crack with respect to the loading direction. For the biaxial case, there is a crack branching happening, a very complex structure, but I don't have any, of course, experimental data to back this up. So this is what the model predicts. And finally, I want to show you the prediction of the model for the macroscopic test data. So what I do here is I plot the true stress strain curves for all the different stress states for this as an example for the first morphology, and I'm extracting the data where the stress starts to drop and the damage initiates. So I'm comparing this to macroscopic damage initiation locus, which is the black curve here. So, and all the circles are from the data from the microscopic analysis for 3 morphologies. So overall, we can see that the shape of the locus is more or less predicted. For the uniaxial case, it is there are some points that are close to the macroscopic predictions, and the others are more far away. For the plane strain tension, not a good agreement is achieved, we can say. So there are possible reasons for this. One is that we are using a plate-like structure, and we don't know out-of-plane grain structure of this model. It's not maybe very representative of the real one. And also we can improve this model, of course, by adding triaxiality or load dependence to the phase field model, but then we are also introducing another parameter identification phase to the model. which is not, of course, desirable. So I want to conclude my presentation. So simulations at the micro scale actually is can be employed for like controlled microstructural analysis without like analyzing the real material. But it requires, of course, very fine tuning of the models and like certain microstructural features that are, of course, detrimental to mechanical performance. And as I said, the current failure model can be improved. However, it also introduces more complexity in terms of parameter identification. So thank you. That's all. I can answer your question.